Integrate the integral secant to the 6th theta tangent squared theta d theta. Let's start by prepping this thing first. This is the indefinite integral of secant of theta raised to the 6th power times the tangent of theta raised to the 2nd power d theta. Now this is a product again. Let's try using a substitution. Our two choices are secant and tangent, and since secant's raised to the bigger power, let's try it first, see if we can get rid of the more problematic power. The derivative would then be secant theta tangent theta. Oops, that should be a d theta down there. Secant theta tangent theta. We can multiply both sides by a d theta to get this differential right here. Does it fit? Well, let's go and rewrite this just to make sure. If we pull a secant theta and a tangent theta out to the side, what we'll have left over is a secant theta to the 5th power and a tangent theta to the 1st power. So yeah, the differential does fit. We can replace this term right here with d theta. We can replace the secant terms by u to the 5th power, and then we have the lonely tangent to take care of. Now remember, the Pythagorean theorem says that the tangent of theta squared plus 1 is the secant of theta squared. And so if we solve this for tangent, we get that tangent of theta is the square root of secant theta quantity squared minus 1. So we can replace this tangent term here with secant of theta quantity squared to the 1/2 power. And then the secant can be replaced with a u. So this becomes u squared minus 1 quantity to the 1/2 power. And this becomes the new integral. If I clean that up a bit, this is the integral of u to the 5 times u squared minus 1 quantity to the 1/2 power du. This is a product integral with that 1/2 power, which means this is a substitution problem. So we'd have to do a second substitution. Let's put this on hold for a second and see whether or not the other substitution works better. If we would have tried u being the tangent of theta instead, then du d theta would have been the secant of theta quantity squared. So multiply through by d theta. And now let's rewrite the integral to make sure that this differential fits. So we'll pull out that secant of theta squared d theta, and then see what we have left over. We're going to have 4 of these secant thetas left over, so secant theta to the 4th power. The tangent part is untouched, so we still have tangent of theta quantity squared. And now we can make the replacements. The differential can be replaced with a du. The tangents can be replaced with u, so we have a u squared. And now we have to get rid of secant to the 4th power. But that's just secant squared squared. So we should have the tangent of squared plus 1 quantity squared. And we can replace the tangents now. So this becomes u squared plus 1, the secant squared part, squared. That's secant to the 4th. Now if we clean up this integral, this becomes u squared times u squared plus 1 quantity squared du. Once again, it's a product integral, but this one can be expanded, and expansion is usually easier. So let's stick with this one instead. So continuing our work up here, let's FOIL out that binomial first. We'll have u squared times u squared squared, or u to the 4th, plus 2 times u squared times 1, plus 1 squared. We can distribute the u squared into this now to get u to the 6th plus 2u to the 4th plus u squared. And now we have a power function, so we just integrate term by term. The first one will get us a 1/7 u to the 7th. The second one will get us, the 2 comes along for the ride, a 1/5 u to the 5th. And the last will give us a 1/3 u to the 3rd. If we back substitute with the winning substitution, we get 1/7 times the tangent of theta raised to the 7th power, plus 2/5 times the tangent of theta raised to the 5th power, plus 1/3 times the tangent of theta quantity cubed. Now I'm not going to simplify this, let's just tack on a plus c, because this is a bit nasty. And so there's our working antiderivative.